Okay, let's get started. Yesterday, we introduced the concept of momentum conservation, and we used for that purpose a very unfortunate collision between Alex and Octave. And they had an incident where Alex's oversized American-sized vehicle collided with Octave's reasonable little French car, and we had the collision occur. And in that collision, Alex's speed went down from 50 kilometers per hour to 38.5, not very much. And Octave was sped up quite a bit from 0 to 38.5. Now, we're going to take a look at that interaction now on a couple of things. First of all, we looked at momentum, and we saw that the momentum was conserved. So a natural question to ask is, well, how about kinetic energy? Is kinetic energy conserved in this interaction? So we have the stuff over here. I'm just going to erase this so we have some space. We're going to remind ourselves of the numbers we used, which was that Octave man, wow, I'm good with the markers. I really should be better with the markers. So Octave, and here was Alex, good. And we had the speeds going from 0 to 38.5 kilometers per hour. And Alex's went from 50 kilometers per hour to 38.5 kilometers per hour. And we also had the masses that we used yesterday. And of course, I erased that just to make it a little more interesting, but I've got it right here, so no biggie. We have a mass for the Hummer of 3,000, and Octave's car, including driver, is just 900, I think. Yep, that's right. So we have here, the mass is 900 kilograms. Whoopsie. And then here, this mass of the Hummer is 3,000 kilograms. Okay, so let's just calculate it. And to calculate it, we need to do a little conversion. So before, here's an important reminder. Well, not a reminder now, but when we do momentum problems, we can use weird units like kilometers per hour, miles per hour, parsecs per millennium, doesn't really matter. And then we're good, we can do that. And as long as our final speed comes out in that same unit and we're happy with that, that's great. But if we're making a conclusion about energy, then we have to make sure we're using a standard unit for velocity, which of course will be meters per second. So we need to convert 50 kilometers per hour to meters per second, and the conversion factor is 3.6. Need to divide that. So if we do that, 50 divided by 3.6 gives us 13.9 meters per second. Good. And then of course, we also need to convert this one, 38.5, divide by 3.6, and we get 10.7 meters per second. So these here are both 10.7 meters per second. And we can now go and find, not just, we have the velocities, we can now take a look at the energies and say, okay, well, let's see what the energies are for those situations. So Alex, of course, 13.9 meters per second. His mass is 3,000 kilograms, not his, but his and the Hummer combined. And of course, our equation for kinetic energy, just a reminder about that, 1/2 mv squared. And using that equation, we can find the energy, 1/2 mv squared, 1/2 3,000 times 13.9 squared. Let's just do that. Pretty straightforward, 1,500 times 13.9 squared. And I get an energy here of 290,000 joules, or 290 kilojoules, for the energy that the Hummer brings to the table. So 1/2 mass times v squared, and of course the energy that Octave had initially was 0. And let's take a look at the final kinetic energy. We'll calculate them separately just because of the way I set up the table. So for the Hummer, 1/2 mv squared, we're now using 10.7. Let's do that, 1500 times 10.7 squared, and I get 172 kilojoules here for the energy of the Hummer. And let's find the energy of the Peugeot. And we got 1/2 900, that's 450, times v squared, 10.7 squared, and I get 52 kilojoules. 52 kilojoules. And you say, okay, at first glance, you might think maybe this is conserved, but of course, when we add these two together, we get 224 kilojoules. Whoopsie, misspelled that. Kilojoules. So, not all the kinetic energy is conserved. Well, first things first, we'll just get a grip on how much of the energy is conserved, and we'll see that we have lost 66 kilojoules, the difference between them, so percentage K lost. They like asking that question, so let's be sure to remember how to do that. So we take the difference between those two values. We've got 66 kilojoules as the amount that was lost. We divide by the original energy, and of course we need to multiply by 100% to then get the answer. 66 divided by 290, and I get 22.8% are lost, or about 23% lost. So, not sure whether you thought that was going to happen, but we can quickly figure out that that makes sense, that the energy should not be conserved because we put some energy in another place. Now, a reminder, what happens in this situation is we have a car colliding with another car. The Hummer hits the Peugeot, and the Peugeot gets embedded basically in the grille of the Hummer right in the front. And in that process, we were exerting a force on the Peugeot, and the Peugeot was exerting a force back on the Hummer. And that process actually deformed both vehicles. More the Peugeot than the Hummer, but definitely the vehicles were deformed. And some of the energy was used up in that process of deforming that metal, and also in making a lot of noise. Car accidents are incredibly noisy, okay? So they're a very loud crash, and there's a lot of energy in there, and that's where the energy went. So in these kind of collisions, we expect this. And these kind of collisions, what exactly does that mean? These kind of collisions are ones where the two objects afterwards are traveling together, and we give those kind of collisions a special name. And we call them perfectly inelastic. Okay, and it's kind of weird that we call it perfectly inelastic because it doesn't seem so great or perfect because you just wrecked the car. It might feel like, oh, wouldn't it be perfect if we didn't wreck the car? But that's what they're called, perfectly inelastic collisions. They're defined by the fact that our two objects afterwards have the same speed. And we can express this in different ways. We can just say V1 equals V2 for the two objects that collided. Objects travel together after the collision. Good. And it's actually showing up. Yeah, it's good enough. It's not really awesome, but it's showing up good enough that you can see it. Now, these pens, okay, two together. I'm not going to rewrite the whole thing because that's a bit much, but there we go, together. Okay, so that's our situation, and we find that some energy is lost, so that's the first thing. We have this thing right here, and then the other thing, though, we'll mark that there, kinetic energy is converted into sound and heat in this kind of collision. And you might think, really, heat as well? Well, the sound, for example, if you think about it, what is sound? Well, sound is just air waves that transmit energy, but they dissipate, they go away. I mean, like once I've talked, right, the room is quiet. Well, that energy goes somewhere. So sound also eventually becomes heat. So really, in the end, everything pretty much gets into heat. That's where everything goes. And you can also talk about it going into the deformation energy of the cars. But either way, it is key that kinetic energy is lost. But of course, it doesn't just disappear. It dissipates, but it doesn't disappear because the overall energy of the universe is still conserved. Okay. And that just means that the end place that energy goes is heat. Okay, cool. I'll take a picture of that, and then we're going to reset for a second to think about where this leaves us. Where that leaves us in terms of momentum in general. So we have up here our starting point, and we've found, okay, that we can use conservation momentum under some circumstances, but I actually tricked you a little bit because I made this problem that I chose intentionally easy. Okay, and let me illustrate that. And it's kind of like one of those, like the magician, like who does the trick before you even pay attention. I used an example where the two cars afterwards travel together, which was a necessary condition for us to be able to solve the problem. Let me explain. Let's think about this problem in general. So we started with one object, and let's just draw it like that. And we say this is M1, okay? And we had it moving at V10, okay? And let's take a second object, and this would be our Hummer with Alex driving it. And then over here we had a second object, okay? And the second object was the Peugeot, and let's call that object M2. Now I made it not move, but we could have made it move. And options would be, it could be moving to the right slower than this one if we want the two objects to collide, or we could make it collide towards it. Let's do that just for fun. Let's do V20 there. Okay. And the first thing we notice is we're still being a little bit simpler here because, of course, if you imagine these are billiard balls, pool balls, for example, they don't have to necessarily hit each other straight on. So we're going to just think about this for a minute, just in terms of being a one-dimensional collision, just to make it a little bit easier. So they collide, and afterwards they're still traveling in the same direction. Good. So we've got our two objects, we're making them hit each other, and then afterwards they're going to also be moving in this direction. Maybe there are two carts on a track, for example, that have to be in that direction. You get the idea. So just from what we know, these two things collide, which means in the collision, they act on each other. But because it's a collision, the only thing that really matters in terms of their momentum changing is the internal forces, the force of the left ball on the right one and the force of the right ball on the left one. And we again have a situation where if we made a little drawing of the energy, the forces on these two, we did this before. So we would say, okay, the force on the right ball, on the red ball, okay, would again look something like this. Okay, it's a force on the right, to the right on the red ball, because the black ball strikes it, and as they collide, those two forces will add those two balls will interact in such a way as that the black ball will exert a force to the right. Initially, it's very small because it's just touching, then it kind of increases to maximum value, and then eventually the collision is over and the value drops down. So this is the F on 2 is in red, and then if we also draw in F on 1 in black, okay, according to Newton's third law, this would be exactly, okay, it was too deep. Here we go. There we go. Would be kind of close enough. It would be the exact opposite of the force on 2. And then, of course, that means that in total, the total force on these two balls is 0. And if the total force is 0, that means that the total impulse delivered to both objects together is 0 by our definition of impulse, right? Impulse is the area underneath the curve, right? No impulse delivered, no momentum change. Therefore, the two balls together have the same momentum. It's conserved. Good. And we can write that out. We can say, all right, this guy has momentum before the collision. And let's stick with the color scheme. So we have M1, V1, 0. That's the momentum before the collision. Then we have M2, V2, 0. That's its momentum before the collision. And that's conserved. Well, what does that mean? It's conserved means after the collision, the sum of the two is still the same. So that means on the right-hand side, of course, we have M1, V1. Plus, we have M2, V2. Now, we wrote this down in one dimension, and we are aware of the fact that it could move in 2 dimensions, so we would then have vector things on there, but for 1 dimension, we don't need those vector arrows on top of there. We also, here's an important note, notice that V20 is to the left, and of course, if we wrote in numbers, we'd have to make V20 negative, okay, to be consistent. V10 is positive, V20 is negative, but either way, in a normal situation, let's assume we know M1, we know V10, we know M2 and V20. So two pool balls approaching each other at a certain speed. We would assume that we know those. And this leaves us with a problem because in this equation, as you notice, we have now 2 unknowns, V1 and V2, the speed of the 2 objects after the collision. So in order to solve this system, we actually need a system. We don't have a system, we just have one equation with 2 unknowns, so we need a second equation, okay? So the second equation could be, and that's the example I gave you, V1 equals V2. If that's true, then this acts as the second equation to allow us to solve this. And we did this because I gave you the fact that Octave's car was embedded in Alex's car. They were traveling together because it was a completely inelastic collision, okay? And that would allow us to progress in that situation. Now, as you might assume, not all collisions are completely inelastic. That's not even an assumption. You know this to be true. A lot of times things bounce off each other, okay? And they do not get embedded in each other, okay? So if we imagine 2 carts on a track and then they bounce off each other, we'd like to know what's true afterwards, okay? So we have to talk about 3 different options for approaching this, okay? The first one I already told you. The second approach runs over kinetic energy. Now, because we're dealing here with inelastic collisions, you might assume correctly that we also have elastic collisions, okay? And elastic collisions are characterized by the fact that kinetic energy is conserved in the collision. Let me just write that down. So what that of course means is that K0 is equal to K. So we're having a collision that's perfectly able to conserve kinetic energy. There's no losses to sound. There's no losses to heat. There's no losses to friction. There's no loss to deformation. It's elastic, so it's a perfectly bouncy situation. So what does that mean in real life? That means that we have the two objects, they bounce off each other perfectly, and there's no loss of kinetic energy. And of course, as you probably already figured out, it's like, wow, that seems really hard to do. And it's pretty much impossible to do, which is why these don't really happen in real life. They're close to happening in some situations, but generally they don't really happen. They only happen in physics problems, so we can then solve the physics problem. Now, before we actually go to the third case, let's just kind of think about what would that actually mean if we were to now use this condition as our second equation. Remember, we have this as our first equation, conservation momentum, right? P0 equals P is our first equation. And now comes our second equation, this one. Now, this one translates into this. Let's see what happens to K0 equals K. Let's actually write it out. And I'm going to just use red. I'm not going to do the black thing anymore, okay? So let's just write it out, and we'll write it out as 1/2 m V1 0 squared plus 1/2 m2 V2 0 squared equals 1/2 m1 V1 squared plus 1/2 m2 V2 squared. We now have two equations, and everything on the left side is just a number. We can calculate those, but on the right side, we have two unknowns, V1 and V2, just like we had in our first equation, two unknowns as well. Now, here's the problem. Two problems. Well, might be three problems. First problem. You take a look at this equation and you see that your solution, your variables over here are squared, okay? So it's easy for you guys to lose track what that means. So I'm going to translate it into X and Y, just because you guys are more familiar with that. Our first equation was a number equals a number times X plus a number times Y, right? Because V1 and V2 are our two unknowns. So our equation 1 could have been something like 17 is equal to 2x plus 3y. Okay, that's like the first equation up here, our momentum conservation equation, that we've now translated into x and y to explain why mathematically we're in trouble right now, even though, well, you probably think you're in trouble anyway, but you get the idea. Let's take the second equation. The second equation is a number, it's probably going to be bigger because of V1 squared, doesn't matter. Let's do 76, right, is equal to x squared plus 3/2 y squared. Okay, now here's the problem. These two equations we have here don't look as nice as we're used to. When we have a system of equations, we know that we can solve it, we being humans, if we have enough equations. Two equations, two unknowns, that's solvable in general. But we have a problem here that if we use our standard method of solving, which would be to take the first equation, solve it for x, for example, and then plug it into the second equation, bad things happen. And specifically, what happens is you have to use binomial to be able to figure out how you plug that in over there, and you get like x squareds and xy's and all kinds of crappy crap, right? So, and the other thing is, in the end, you're going to get a quadratic equation. And this is just bad news and makes everybody unhappy, including us who has to grade this. So this is going to be a problem, and we will not expect you, the royal we and AP Physics writers and readers will not expect you to solve that, because you don't want to solve it, we don't want to grade it. That's just it, okay? That's going to be bad. Theoretically, it's problematic. So in practice, this means that most likely they will not ask you a question that is actually an elastic collision, okay? Because this is just crap. So they're not going to ask you to do that. However, even though this is true, we kind of put a big old line through it. Not going to happen, okay? Instead, we can use a little trick. Now, and the little trick is that if this is true, it is also true, and this is a little bit surprising, that in the collision, the relative speed of the objects flips signs, okay? You might be like, what does that even mean? I'll write it out for you. This means that V20 minus V10, this thing is the relative speed of the two objects. That's equal to minus V2 minus V1. That's great pedagogy. I wrote it really, really small in the corner. So here we go. So the relative speed before the collision, the difference between V20 and V10, is the opposite, negative, of the relative speed after the collision, V2 minus V1. And I'll rewrite it down here just because it is important. So what I want you to do on a test, if this happens and it is an elastic collision, kinetic energy is conserved, I want you to write specifically this. You say K0 equals K, therefore V20 minus V10 equals minus V2 minus V1. Now, this is a way for me to remember this, because I remember it through the fact that the relative speed flips signs. However, of course, the minus sign will get distributed in here, and you can rewrite it as V20 minus V10 equals V1 minus V2. You can also remember it like this. And for you guys, with all due respect, there's a reasonable chance that when you distribute the minus sign, bad things will happen. So maybe you want to remember it like this, whichever works for you. And again, it is unlikely that we will ask you to do this on the test, but officially you're responsible for it. So it could happen. So I want to make sure we talk about it. Okay, so in our case, we could actually do this. So let's actually come back to our situation with Octave and Alex. And let's imagine that that situation was elastic, and let's figure things out. Okay, I'm going to take a picture of this stuff here and put it in the group. So we're going to now pretend that Alex Octave is elastic. Okay, so we're putting them basically in perfect bumper carts. Okay, so they're perfect bumper carts. They have beautiful magnetic springs, basically big old magnets on the end that allow them to soundlessly interact and bounce perfectly off them. Okay. So there we go. An elastic collision and elastic collision. Good. So just a reminder about what we had previously. We had M1 is equal to 3,000. We had M2 equals 900. We had V10 is equal to 13.9 meters per second. 13.9 meters per second. And we had V20 equals 0. Cool. That's our starting point, and we can now go and write this into our equation. So we've got two equations now, okay? So we have in the collision momentum being conserved, so we can write out that M1 V10 plus M2 V20 equals M1 V1 plus M2 V2. And of course, this is because P0 is equal to P. And there we go. There's our first equation. And let's just write it out because we can. So we got 3,000 times 13.9. M2 V20 is 0. Alrighty, so we can actually work out this value, 3,000 times 13.9 times 13.9, and we get 41.7 kilojoule, sorry, it's not kilojoules, 41,700, and that's equal to M1, sorry, 3,000 V1 plus 900 V2. Okay, so here's our first equation. There it is. And now we're going to write out our second equation. Okay, so let's take a look at our second equation. Again, our second equation is due to the fact that kinetic energy is conserved. We've been told kinetic energy is conserved. So these are the same, and we will be good physics students hoping to get points on the AP exam by now indicating that because this is true, that it's true that V20 minus V10 equals, and we'll write it down the way that I told you to maybe remember it, like this, that this is true. Okay, and let's plug in values. V20 is known to be 13.9. V10 is 0. We can drop that. And then we have V1 here and V2. And at this point, you should breathe a sigh of relief because this equation now is super solvable for one variable. And V1 is just saying, come on, let's go. We're going to solve this for V1, right? And then V1, of course, is equal to V2 plus 13.9. Wow, that was easy. We solved it. Boom, there it is. And now we can plug it into the other equation and get a solution to this problem rather easily. Okay, so let's take a look. We've got our first equation. We're going to plug that in. We're using our standard method for solving systems of equations. We've solved one, and now we're going to plug it into the other equation. Let's do that. We're on screen over here. So we have 41,700. There we go. Is equal to 3,000. And V1 is now equal to V2 plus 13.9. We plug in for V1. And then we have here plus 900 times V2. There we go. Okay, so now we have one equation with one unknown, so just a math problem at this point. And let's actually multiply it out. We got 41,700 on the left. We got 3,000 V2 and 900 V2 is 3,900 V2. Plus we have 3,000 times 13.9. Wait a minute. Something's wrong. Okay. Okay. I made a mistake. Hang on a second. I'm getting out 41,000. Hang on. Relax. What happened here? So if that's conserved, 13.9 is the starting speed. V20 is 0.
Is 13.9 negative? Because we have V20, which is 0 minus V10.
Thank you. Excellent. Thank you. That's right. See how easy it is to mess this up? I put that in there on purpose. Ha, 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 ha. Thank you. 41,700. Now we're good. Good. Cool. So that should be negative there. I made the mistake. And that comes back to V1 equals V2. Yeah, exactly. Yeah. Right. Right? V1 minus V2. So V1 equals, wait a minute. V20 minus V10 equals V1 minus V2. V20. Oh, yeah, that's where the negative sign is. Here. Because V1, 0 is 13.9. That's the minus sign. That's where it got messed up. That's where it got messed up. Correct. Because V10 is 13.9. V20 minus V10 is minus 13.9. Cool. Great. Cool. Okay. So let's see where we are now. So we have then move all the numbers to one side and keep the variable on the other side. We get 83,400 equals 3,900 times V2. And of course, this means that V2 after the collision is 83,400 divided by 3,900. And we get 21.4 meters per second. So we have found that our little car, okay, that's the Peugeot, is after the collision moving at over 21 meters per second to the right. Notice a couple things. First of all, this is now a bigger speed than the car had before, and it's also a bigger speed than the Hummer brought to the situation. The Hummer came in at 13.9, and now the Peugeot is moving at 21.4 meters per second, which means that this is actually a more drastic change for Octave. It's actually not better, it's worse. Just stating that. So this is actually greater than V10. Good. Second thing is, let's find the speed for the Hummer. And the speed for the Hummer, of course, we have this equation of V1 equals V2 minus 13.9. We can use that now to use V1 equals V2, 21.4. Let's plug that in. V1 is equal to V2, which is 21.4, minus 13.9, and we get 7.5 meters per second. 7.5 meters per second for the speed of the Hummer. The Hummer is still moving to the right, but it's slowed down, and it's actually slowed down more than it slowed down in the previous situation, because in the previous situation, it slowed down to, just a little bit. Previously, it slowed down to 10.7. Now it's slowing down to 7.5 meters per second. And in this case, kinetic energy is conserved, but the effect is Alex slows down even more. Octave actually moves even faster. And what does that mean? That means, of course, because the change in velocity is greater for both, the forces on each of them is actually also bigger. So that means that this interaction is actually probably a little bit more dangerous than previously, which is a little bit surprising because you think, whoa, wait, maybe this wouldn't be that bad because it's bouncy, but it's actually worse, okay? So that's why we construct cars to actually do exactly what we described earlier, to construct cars that actually have crumple zones that actually absorb the energy and actually get all squished up and then protect the people who are in the compartment in the center. And then the car can be thrown away afterwards and hopefully the people just walk away. That's the plan. So works pretty well. Does not work so well for bouncy things. So that's it for today for the elastic collision situation. And tomorrow, we'll look at the third case. Tomorrow we have 7th period, and I will do the introduction for that now. I will now stop the video Is it still recording? I don't even know if it's still recording. It is still recording. Okay, let's go up here. And